Okay, so let's continue with emission spectrum, which is the second part of the unit, continuing with S1.3. So today we will talk about emission spectrum. So we know that when in an atom, let's say this is an atom, this is the nucleus, and this is the orbit. And we know that in the orbit, electrons, they keep on revolving, right? Let's say this is an electron. So there is another orbit, right? The dotted line shows that there is another orbit. Let me put it here. Okay, you can see this is the bigger orbit. Let me draw it like this, right? Okay, so when let's say this electron has gained energy from the surrounding, okay, they got the energy from the surrounding, they are absorbing the energy. Once they absorb, what it happened, it the electron leave their shell, their energy level, and move to the next level. So let's say that electron has gone to the next level, next higher level. This is called excited state, and this is you can say ground state. So when the electron absorb energy and move to the next level, that is absorption spectrum. That's absorption diagram. And let's say when electron have to come back, right? So when they have to come back to the original state, what will happen? Whatever electron or whatever energy they have gained, they have to release it out, right? So when they are releasing, the electrons is finally coming back to the original state, and we call them spectrum. So when they gain energy, they are absorbing and they are going to the next level. And when they are releasing the energy, they come back to the original state. That's emission spectrum, right? So we can say that electrons moves rapidly around the nucleus in energy shell. Now what is energy shell? This is energy shell. This is also an energy shell, right? So if their energy is increased, what happened? The electron jumps from next to the next orbit, right? So we can say if their energy is increased, the arrow up shows increase, then they jump to the higher energy level, right? So but this process is not permanent, it's reversible process. Why reversible? Because electron can come back to the original. So we can say so electron can return to their original energy level. And when this happen, they release energy. You can say when this happens, they emit energy, right? Now this energy is, when we say energy, so the frequency of energy is exactly the same. So it's just being emitted rather than absorbed, right? So we can say that the frequency of energy is exactly the same. It is just being emitted rather than absorbed, right? So what we can conclude here, that whenever electrons gain energy from the surrounding, they move to the next level, next orbit, and when they have to come back, it will release the energy, and these energies have certain frequencies, right? So the energy they emit, right, is a mixture, not of one, mixture of different frequency, right? This is though to correspond to many possibilities of electrons jumping, right? So if the emitted energy is invisible, right, it can be analyzed very easily, right? So results in, and what will happen, these emitted lights or emitted energy of different frequency result in result in line emission spectrum, right? So now let's discuss about hydrogen spectrum. Why I'm saying hydrogen spectrum? Because here we will see when the light from when the electron of the hydrogen atom is going from higher to lower energy, then what kind of uh, emission spectrum it's going to form. So we'll discuss about those possibilities here, right? How and what, in what way it goes. Let's say, suppose this is an ground level, this is nucleus. Let's say this is level 1 or shell 1. This is, let's say, shell 2. This is shell 3. This is shell 4. This is shell 5. This is shell 6. This is shell 7, right? And in this way we have an infinite number of shells, right? So these are number of shells, right? Okay. So let's say that the electrons are coming back from infinity to the orbit 1, or you can say from orbit number 7 to 1, or 6 to 1, 5 to 1, 4 to 1, 3 to 1, or 2 to 1, right? If let's say this is the condition, so a light of packet of light is released, and this is called Lyman series. And the Lyman series are actually a UV light. Okay, let's say the packet of light or electrons is jumping from infinity to, let's say, orbit number 2, second shell, or it's jumping from level 7 to 2, 6 to 2, 5 to 2, 4 to 2, or let's say 3 to 2. In this case, the light which is released, energy which is released, we consider them as a Balmer series, and these are visible light. Let's say the packet of energy, a packet of light is released when electron jump from infinity to, let's say, orbit 3, maybe in infinity to 3, or 7 to 3, or 6 to 3, 5 to 3, or 4 to 3. This is called Paston series, and these are infrared rays. Let's take an example that electron jump from infinity to level 4, or from 7 to 4, or from 6 to 4, 5 to 4. This is Bract, and this is again an infrared radiation. And let's say if electron jump from infinity to level 5, energy level 5, or 7 to 5, or 6 to 5, they release a packet of light, packet of, it's called P fund. Again, this is an IR radiations, right? So what we are seeing here, that each line in this series is a specific energy level. So this suggests that electron can only possess a limited choice of allowed energies, like you can see UV, visible, IR. So these packets of energy is called quanta. I'm writing some points also. So each line is a specific energy, right? And they comes in packet. So these packets of energy is quanta, right? So when what you should notice about the spectrum is that the lines get close together towards end, right? So this is called convergence, and the set of lines is called converging towards the higher energy. So the electron is reaching a maximum amount of energy. This is correspond to ionization energy of the electrons, right? So I can just add this point, that what you should notice about the spectrum is that the line get closer together, where towards the blue end of the spectrum. This is convergence, and set of lines is converging towards the higher energy end. right? So the electrons is reaching a maximum amount of energy, right? So this correspond to what we call them, correspond this maximum corresponds to ionization energy of electron, right? IE, ionization energy. So these lines are first uh, seen by these scientists, right? Balmer, and they have named it him according to him, right? So what we have seen in this particular section is when uh, light, right? When an electron, actually an electron. So so this was an what we can see here in this diagram, that the line spectrum, right? The line emission spectrum, right, of hydrogen provide an evidence, right? Evidence of these energy level, and it was deduced that the families of line correspond to electron jump from higher to lower shell. That means all these packets of light, let me circle this, these all are same, these all are same, these all are same, there is no difference whether jumping from infinity to 1 or 2 to 1, the nature is same, right? So what we have concluded, that these energies, these frequencies are specific, right? Okay, so let's go up a bit. So here we can see that what is Lyman series. It's a series of energy or frequency generated when electron jump from infinity to 1, right? Or 2 to 1, right? Infinity to 1 or 7 to 1 or whatever. Then Balmer series, electron jump from infinity to 2, or you can say least is 3 to 2, right? What is the nature of light? This is visible, and this is UV. Then third we have seen Bastion. Here what electron jumps from infinity to third shell, or 4 to 3. They are infrared. Then Bract, what we have seen here, here electrons are jumping from infinity to 4, or 5 to 4. They are again infrared. So these are the different wavelengths of light. So is uh, is generated, right, when the electron jumps from higher to lower. So the finding helped scientists to understand how electron works, right? So this gives a working model and also provide a backbone to the knowledge of shells, subshells, orbitals, right? And also provide the backbone to our knowledge of energy level, which we call them shell, right? Subcells and orbitals, right? So these gives a clear idea. So what conclusion we have drawn is that, let's say we are talking about jumpings, right? So let's say here is a jump, here is a region, and here is the energy. So jumping is from, let's say, from infinity to, let's say, shell number 3. Region will be IR and energy will be very low. Let's say if I'm talking about infinity to 2, this becomes visible, and they have a medium. So energy is going down actually. Let's say infinity to 1, this is UV, this is very high, right? So one multiple choice question you can expect from here. So before going to the next topic, let's have one question. Question is, which electron transition in hydrogen atom spectrum emit visible light? Let's say I'm giving an option A, n equals to 1, n is the number of shell, to 2, B, n 2 to n 3, n 2, n 1, n 3, n 2. So what we have seen, we need visible light, right? And visible light we are getting here, you can see here I have written, so visible light we are getting when electron jumps from either infinity to 2 or 3 to 2, right? So here it's 3 to 2, this is the correct option. So emission in the visible region occurs from electron jump from any higher level to level 2. This is not possible because how this electron is going is not coming back, it's going to the next level. Again, this is not right. Of course, this is not right. So this is correct, right? So that's it for this lesson. In the next lesson, we'll talk about electronic configuration and we'll discuss more about other things. Till now, thank you. Stay in touch.